Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, minimum number of arrows to burst balloons. So basically we have balloons on a flat wall that represent the XY plane. And these balloons represent a 2D array integer, where each of them, we represent them by basically the starting point and the ending point of the horizontal diameter of the balloon. So let's say this is a balloon, this would be the start position, this would be the end position of the diameter. And you do not know the y coordinates, like you don't know if like the balloon is here, it's down here, you only know the x axis coordinates, okay? And an arrow can be shot up basically when you have a balloon, like here, you have an arrow that can be shot up vertically in the positive y direction. So it can be shot up like this. Sorry about that. It's not. It can be shot up basically like this, okay? Vertically. And there is no limit to the number of arrows that can be shot. And the shot basically can travel up indefinitely. So what that means basically, if you have a balloon here, maybe you have a balloon here, and you have an arrow that gets shot like this, it will burst all three because it just keeps going up. And what is the goal of the problem of all of this is to return the minimum number of arrows we can use to burst all the balloons. Okay, so now the first thing, let's look at just what this will look like. So just to clarify, I saw this in the Leetcode discussion, and I think it's a helpful drawing. Basically, you have the balloons represented on an x-axis like this here. And we don't care really about the y direction because why do we don't care about the y position? Because as you can see, the arrows here just keep going up, right? So it doesn't matter whether the balloon is down here or up here. It will end up, if the arrow is going from the same x position, it will end up touching it, right? So that's the idea, and you can think of them like this, and the arrow keeps going up, so it will, for example, in this case, it will burst this green one and this red one. In this case, it will burst the yellow one, the green one. If you have another one here, it will burst it. Okay? Now some observations regarding this. So first observation is that it doesn't matter which y position the balloon is in. That's what I mentioned earlier, because the arrow will just keep going up. So keep going up, so it doesn't matter which position the balloon y is in. Here for this green one, if it was in this position, the arrow will still burst it. If it was in this position, like here, the arrow will still burst it. If it was even way up, like here, the arrow will still burst the balloon. So it doesn't matter the y position. So we don't even need to worry about the y position. So we can just consider the x coordinate. And what we need to know is just how many arrows we need to cover all balloons, right? All the x positions of the balloons cover. And so what this means, if there is an intersection on the x-axis between two balloons, we can use just one arrow. We don't need to use multiple arrows. So if we take a look, for example, at the first example here, for the two intervals that we have, 2, 8, this one 2, 8, and 2, 8 and 1, 6, right? They intersect. So we can just use one arrow to touch the two in any intersection. So let's say, for example, we pick the last one and do an arrow like this. This will burst 2. We don't need to do 2 arrows. Let's say, for example, we can do one here and an arrow here. But this is useless. Like, we can do it with just one. We can do it with just one like this. So what this tells you is that if there is any intersection between two balloons, they can share an arrow. And this can be extended even to 3 intervals. So for example, here, with this 2 to 8, 1 to 6, and 7 to 12. 7 to 12, can we do 7 to 12? Yes, 7 to 12. So we could maybe do one that intersects both here, but the problem is it won't intersect this one. So we have the choice either to do one here, and then one here. Okay, this is 2. Or to do one here, so that it intersects the 2. And then to do one that intersects these 2 together, right? And this way we have just 2. And this is actually the optimal way, is just we need 2. So if you think about the approach I did here to optimize, what did I do? Well, I burst the balloon at the end position of each of the intervals, so that if there is one that intersect with it, we increase the chance of it bursting it, right? But it doesn't make sense, let's say for this one, it makes sense to do the end of the first value, the smallest end position, because if I do it for the bigger one, then I won't touch this one, right? And that's exactly your intuition, the intuition to sort by end positions, because I can take advantage of that and use the last position for the smallest end, the last value, the smallest end position, and use an arrow there, because if that balloon intersects with any other balloon, that will touch it, that will burst it, and just keep doing that. And so that's where the idea of sorting by the end position comes in. So that's what we'll apply. And so if we do it for this first example and sort by end position, then we would have 1 to 6, 2 to 8, 7 to 10, and 10 to 16. Now, what did we do here in the example? Well, what did we do is basically, if the start position is less than the last end position, the latest end position we had, we don't need to increment the count of the arrows. We can just use the previous arrow. And so let's just apply it here. So initially, our count is 0. Initially, we are at the first position. And initially, our last end is 0, -1, let's say. And only if start is bigger than the last end position that we increment, that we need a new arrow. Why? Because if the starting position of the new interval is smaller or equal to the last ending position, then that previous arrow just covers it, right? Which is the case here. For example, this start position is smaller than this ending position, and so the same arrow can just burst the 2. Okay, and let's just make sure this is accurate, small or equal. Okay, and so here 1 to 6, we need a balloon at the start because there is nothing before, and so let's count by 1, and the last end is now 6. This is after sorting by end, by the way. Okay, so now we go to the next interval, 2 to 8. Well, 8 is actually 2, which is the start position, is smaller than 6. So that means basically this here can be covered by the same arrow, because this position is smaller than the end, so one arrow can cover both, either here or here. Okay, and so we can basically just keep the same count. We don't need a new one, but the last end is still the same, because we will need the arrow to be here so that it covers the first one. So let's keep the last end as is, and we go to the next one. Okay, so now the next one, the starting position is 7, which is bigger than the last end, which means we need a new arrow, right? And so we need a new arrow here, and the last ending position is 12. Okay, so now we have this here, this one. Last ending position is here, so we have an arrow that goes here. Now, when we go to the next one like this, well, 10 is smaller than 12. So that means there is an intersection. So that means one arrow can cover both. One arrow here at the end of this one can cover both. And so that means we don't need to increment. We are in this case, and we keep going. And that's pretty much it. You can try it on other examples, but this approach should work on all of them. And so let's just implement it and make sure it passes. So this is a greedy sorting approach. Let's do it. So first we need to sort our points by the ending position. Okay, so let's have a key here. Lambda x -1. Okay, and then we said initially we have count and we need the last end. Now let's just initialize them because with the first interval, because we know the first interval there is nothing before, so then there is nothing that it intersects with, and we do need to burst this first balloon. And so let's start with one arrow that goes at the ending position of the first point, but -1 here because, or 1 here because we want, this is the ending position, right? And then we can go through the rest of the balloons, so points 1, and then we check. We just do the check that we did here. So let's actually do it. We only increment if this next balloon doesn't intersect with the previous one. So only if this is the case that we do count +1, but we also need to update our last ending position with end. Then at the end we return count. So pretty simple implementation, except this needs to be S. And looks like it passes. And it gets accepted. Okay, that's pretty much it. So yeah, you just have to visualize and see if you have something like this with an interval, you can try a couple of egregious solutions with a couple of sorting mechanisms. Sometimes it's easier to sort by the size of the interval, sometimes by starting point, sometimes by ending point. So you need to think about basically which one works. Now this one as well is probably can be solved with swipe algorithm technique, so just an exercise for you to try. And in terms of time complexity, this is linear in the length of points, so it's O(n). Yeah, and that's pretty much, and it's linear here for this loop O(n), but the sorting is O(n) log n. So overall it's O(n) log n time, and in terms of space, it's O(1), because we are not really using any extra array or an extra space. Yeah, so that's pretty much it. Thanks for watching, and see you on the next one. Bye.